Just uh, an announcement about homework 2. It was originally supposed to be available today. We've decided to release it on Tuesday instead of today. This homework will touch upon some theory around linear models and mistake-bound algorithms. And you'll be implementing the perceptron algorithm and its variants in your experiments. And the protocol is going to be the same. You'll be submitting things on your autograder, and a lot of the code that you wrote for homework 1 is going to be useful again, in particular cross-validation and such things. And if you had trouble with cross-validation for homework 1, there's another chance to you can have another go at it. And you'll be doing cross-validation for pretty much every homework, and you'll be doing that for your project as well. So it makes some sense to carry over code from one homework to another. Yes.
Is the due date still the same for?
No. We'll give you 2 weeks.
Okay.
So we're going to adjust all the due dates. We're still kind of figuring out the way to make everything fit within the semester. Keep an eye out. There'll be an announcement on Tuesday.
Okay.
Yeah, you'll get 2 weeks for this homework as well. Any other questions? So what that means is you get a weekend off without a homework, and I feel really bad for that because,
Yeah.
no, but I feel like you ought to have that something to do in the weekend. In any case, I'm sure you'll find something to do. Let's jump back to where we were. Yes. My TA is laughing at me. It will be graded. I cannot give you a concrete time. It's going to take some time to make sure that the pipeline gets of grading happens. I don't want to give you a concrete timeline. My hope, now my TA is avoiding my eye contact. My hope is that we get you feedback on homework 1 before you submit homework 2. That way you have a sense of what we are looking for. Other questions? If not, we're going to continue with the mistake-bound learning protocol that we started in the last lecture. We were looking at this particular way in which the learner and the concept or the teacher interact with each other. Mistake-driven learning proceeds in rounds. Each round involves the exact same process. The learner first receives an example without a label called X here on the slide. And before it learns anything else about the label, it first has to commit to a prediction. It makes a prediction using its internal hypothesis, which is called H sub t here. And after it makes the prediction, it receives the true label. Nature provides the real label to the learner. And then if it turns out the prediction was incorrect, then the learner has the opportunity to update its internal hypothesis from HT to HT plus 1. So the entirety of this protocol is defined by how the prediction is made in step 2 and how the update is done if there's a mistake. So this is a very simple protocol. And the other thing that we saw in the last lecture was a certain definition. We saw this definition of something called a mistake-bound algorithm. An algorithm is a mistake-bound algorithm for a certain concept class. See, a concept class is nothing but a set of functions. An algorithm is called a mistake-bound algorithm for a certain concept class if the number of mistakes it makes on any sequence of examples that are provided to it for any function picked from the concept class is no more than some polynomial in the dimensionality. So the intuitive idea here is nature or an adversary has the freedom to pick the worst concept before learning starts, and it has the freedom to choose the very worst sequence of examples. And in this case, the worst sequence of examples would be the ones that force the learner not to make mistakes for a very long time because it does not get to learn. The adversary can choose a bad sequence of examples and a bad concept, and yet the learner the algorithm A makes a mistake, makes only a polynomial number of mistakes, polynomial in the dimensionality. If the algorithm does that, we call that a mistake bound algorithm. There is a bound on the number of mistakes. And there's also a problem. The other thing that we can think about is something about concept classes themselves. If you have a set of functions, you can ask, is this a difficult set of functions to learn? In other words, if I tell you that my true function is inside the set and I ask you to figure it out somehow, the question to think about is this a very difficult set of functions to explore? And for that, we have another definition. The concept class C is said to be learnable in this model if there exists some algorithm. We don't care whether we can even, maybe we may not be able to actually execute that algorithm, but at least we can state the existence of it, provably. If there exists some algorithm, that is a mistake bound algorithm. In other words, that there exists some algorithm that makes only a polynomial number of mistakes for any function inside this set, irrespective of the sequence in which the examples are presented. So we saw these two definitions, and I mentioned multiple times, just because I want to give something a name does not mean that becomes interesting. Just because I define a concept class to be mistake bound concept class does not mean such a concept class exists. Maybe there is no set of functions that can be learned with only a polynomial number of mistakes. Maybe there's no algorithm that can do this for even one concept class. To point out that to kind of develop a tool for showing that some concept classes are mistake bound learnables, we looked at an algorithm called halving. The halving algorithm is a very simple algorithm. It looks something like this. So it applies only for finite concept classes, which is an important thing to note, because essentially what it does is every time there's a mistake that's made, it removes at least half of the set that's still in consideration. It starts off with a full set of functions, and to make a prediction, remember, to define a mistake-driven algorithm, I need to define two things. How's the prediction done? How's the update done? The halving algorithm does the prediction in the following way. A new example comes in, X here. It has a set of functions currently that are currently in play. It asks every one of those functions, what's the label for this example? And if more functions say 1 then 0, then it predicts 1. If more functions say 0 then 1, then it predicts 0. In other words, it predicts the label that the majority of the set of functions say. Okay, that's the prediction step. And the update step is, if there's a mistake, it removes all the functions that made the mistaken prediction. It predicts using a majority. As a result, if it makes a mistake, then the majority of functions get removed. So every time there is an update, the size of the set of functions at least shrinks by half. Shrinks by at least half, possibly more. Every update causes the set of functions to shrink by half, which means, and I'm not going to revisit the proof, means that the number of mistakes that are going to be made by the halving algorithm is at most log of size of C, where C is the concept class. This is where we stopped in the last lecture. Any questions about any of this? Also on Zoom. If not, let's look at why this is an interesting algorithm. I'll tell you first, before we talk about why it's interesting, I'll tell you why it's uninteresting or impractical. You have to keep an entire set of functions in memory. This set of functions could be exponentially large in the dimensionality. So it's an impractical algorithm to implement. Do not ever implement the halving algorithm. Well, go for try it. It's going to be rough. Don't do it. So it's not a practical algorithm, but it's a proof of concept. The reason halving is interesting is because halving is something called optimal. And we're not proving this, but for certain classes of functions, halving is optimal. In particular, for Boolean functions, halving is optimal in terms of the number of mistakes that it makes. What I mean by optimal is for that set of functions, for example, for Boolean functions, irrespective of which concept is the true concept, irrespective of what the sequence of examples you choose, the optimal algorithm makes the smallest number of mistakes. In other words, if halving makes a certain number of mistakes for a Boolean concept class, no other algorithm makes fewer than that, fewer mistakes than that. The reason that's interesting is if halving makes a certain number of mistakes and that number is more than polynomial, it's exponential, that means there does not exist any algorithm that can do better than that, which means that concept class cannot be learned in the mistake bound model. And that's the reason this algorithm is interesting. It's an analysis tool that allows us to say certain things cannot be learned. We'll see an example of that very shortly. There's a more general definition of optimality that I'm not going to talk about because it's actually even harder to compute. It involves future examples and expected error. Let's not go there today. So to quickly wrap up the definition of this halving, or the part about this halving algorithm, it's a simple algorithm for finite concept classes where we store a set of hypotheses that are still in contention. Every time we need to make a prediction, we ask all of these hypotheses for the label and pick the majority label. If there's a mistake, we get rid of the majority set and we keep a smaller set. And it makes order of log size of C mistakes. And it's optimal in a certain definition of optimal, but not in a different definition. But for the purposes of our discussion with mistake bound modeling, with the mistake bound model, this is good enough. So now, rather than actually talking about this in the abstract, let's look at classes of functions and apply this mistake bound, the halving algorithm's mistake bound to it to see what comes out. Okay, that's the plan for now. Any questions about where we are? For each of these classes, each of these examples, concept classes we'll see, if it turns out that halving makes an exponential number of mistakes, because halving is optimal, we cannot do better than that. No other algorithm can do better than that. If it turns out halving makes a polynomial number of mistakes, that means the concept class can be learned by halving in the mistake bound model, but halving is not practical. So that poses a challenge, a technical challenge. Can you invent an algorithm that's both efficient and matches the mistake bound that halving can do? So to start things off, let's look at this set of conjunctions. A conjunction is nothing but a Boolean function that says that's the AND of a collection of variables. For to make things general, we'll also allow negation. So you have a conjunction like x2 and x3 and x4 and x5 and x100. That's F on the screen. x1 and x2 is a conjunction. x1 and not x2 is also a conjunction. The way I read this is not and this is and. And x1 and not x2 means the label is true if x1 is true and x2 is false. And only then is the label true. In all other cases, the label is false. So it's a simple class of functions. So the game that we are going to play is, we'll do this multiple times, not just here, but also for other ways of analyzing learning. The game we are going to play is we care to measure log size of C, log to the base 2, but don't care about that. Which means the interesting thing here is the size of C. If C is the set of all possible conjunctions, the size of C is the number of all possible conjunctions. If you have n features, how many conjunctions are there? Can someone guess? I'll give you an example while you're thinking. If I have only one feature, I have a conjunction that is saying just x1. Or let's take 2, because 1 is a bit of a weird edge case. I have a conjunction that's x1 and x2. If you have two features, I have x1 and not x2, not x1 and x2, not x1 and not x2, but also x1 itself is a conjunction, not x1 is a conjunction, x2, not x2. And there's one more, which is saying, no matter what comes in, I'm going to say true. I don't look at any feature, I'll just say true all the time. How many conjunctions do I have?
I have a question.
Yes.
Would there also be just a choose false regardless?
No. Sorry? Okay, I'll come back to you, but here you do not have a choose false regardless, because that would be like the base case for a disjunction.
Oh, okay.
Okay, so here we have 9 functions. You have 4 of these, 2 here, 2 here, and 1. This is for 2 features. How many conjunctions would exist if you have n features? Why? So there's a suggestion, 3 power n. Why?
You can either select x1 variable, x variable, or none of this.
Yes.
So 3 possibilities. And if there are n variables, so
You can select x1 or x2 or none of these. Is that what you're saying? Your argument is not quite right. Your answer is right, it turns out. Does someone else want to pick up from that? The answer is 3 power n. The answer is actually 3 power n. So, but your argument is not exactly right. Why are there 3 power n conjunctions? In this case, why are there 3 square? Where n is 2, you have 3 square.
induction also we can.
Okay, you can prove by induction. Induction is a boring method. Let me give you a simple argument here, okay? I have n features, right? Let's think about what a conjunction looks like. A conjunction is something and something and something all the way through. In the first position, let's call that the position where I can choose to put x1. That is the position for the first feature. I can put an x1 here, or I can put a not x1 here, or I can choose to put nothing, which is actually equivalent to putting true. In the second place, I can put an x2 or a not x2 or a true. Here I can put an x3 or not x3 or true, and so on. I have the nth position, xn, not xn, or true. I have 3 options here, 3 options here. In each position, I have 3 options. I have n such positions. So 3 times, I'm multiplying n 3s together, 3 power n. For each position, I can choose an x1 or not x1, or choose to not put that variable at all. And there is no other way, there's nothing there's no conjunction that does not fit one of these templates. So the number of conjunctions is 3 power n. Any questions?
So basically, there's 3 possible options per feature that's in this.
Per position, yeah,
Yeah,
per
per
feature.
position.
Yes, that's right. But that's not the end of the game. The goal is not just to count the number of functions, but to take the log of that. Right? The number of mistakes halving will make is log of the size of the concept class. So log of 3 power n is really n log 3, which is, we can ignore the constants, it's order of n. So that means the halving algorithm will only make as many mistakes as the number of features. Importantly, it's a polynomial. It's a polynomial in the dimensionality. So conjunctions, so the conclusion here is conjunctions can be learned by halving under the mistake bound model. Conjunctions are a set of functions that are learnable. Halving can learn the learnable as defined under the way we defined it. So the concept class of conjunctions is learnable in the mistake bound model because there exists one algorithm, namely halving, that can learn it with only a polynomial number of mistakes. In fact, it's a linear number of mistakes, the simplest polynomial. Any questions about this? I mean, any questions about how we counted the number of conjunctions or the discussion after that? Yes.
So our question, right? We are talking about halving and conjunction. You said possibility of whatever the mistake. It might be possible that at least from then one should be true.
Yes.
Right?
One conjunction.
Saying almost log of all set that we are talking about. How, I mean, why we are not saying that edge is -1, that could be possible reason.
Yeah, it's order of n. This is, the n minus 1 is order of n. So we don't care about the constants here. A friend of mine, former colleague, used to say, "What's a constant among friends?" So what we have here is an interesting statement. Conjunctions are learnable in the mistake bound model. Only a linear number of mistakes, but I haven't shown you an algorithm, or have I, that actually learns conjunctions. I've told you that conjunctions are learnable by the halving algorithm, but the halving algorithm is a lousy algorithm. You shouldn't be implementing that because think about implementing halving for conjunctions. There are 3 power n conjunctions out there. So if you have 100 features, you will store an array of 3 power n, 3 power 100 things. And then you will trim it by half each time. Good luck storing 3 power 100. And if you feel like 3 power 100 is okay, let's see that scale to 1,000,000. So clearly, halving is an inefficient algorithm. So now there's a challenge. In theory, conjunctions can be learned efficiently, in data efficiently, with only a linear number of mistakes. Can they also be learned efficiently from the computational point of view? In other words, is there a learning algorithm that can learn conjunction efficiently? It turns out we've already seen such an algorithm. Remember when I was talking about whether learning is good or not, how good a learning algorithm is, I introduced this idea of an elimination algorithm, where you first only take all the positive examples and look at all the features that are present in the positive examples, and that's the answer. If you want a reminder, it's a slide that looks like this. You only look at the examples that have a label 1, and then look at the columns here that are 1 across all the examples. And this is a super efficient algorithm because you just read the data set, remove all the examples that have a label false, and then for every feature, go one at a time. This is not exactly a mistake bound algorithm, but you can think of going through the positive examples one at a time, and you can convert this into this idea into a mistake driven algorithm. So it turns out there exists an efficient learning algorithm that can match this bound. So effectively, we've solved the problem of learning conjunctions, both in theory and in practice. We're not going to talk about the details of this, but that's about conjunction. Now let's look at a different set. Now we're going to look at a set of functions called K conjunctions. A K conjunction is a subset of conjunctions. So the way it works is you have n features. Any concept in a K conjunction only uses K of those features, at most K of those features, no more than that. Some K. We do not know which K features are relevant, because if we did, then we have solved the problem. So in addition to knowing which conjunction is relevant, we also need to know which of the features are relevant. So a K conjunction, for instance, if you have 5 features, x1 through x5, and a 3 conjunction might be x1 and x2 and not x3. But x1 and x2 and x3 and x4 will not belong to that set because it has 4 things. So you can have at most K. Okay. Now, again, the way to apply this halving algorithm bound is to ask again, how many K conjunctions are there? And I'll tell you the answer, because if you the answer is it's 2 power k and choose k. Why? Why is the number of k conjunctions 2 power k and choose k? Yes.
The 2 to the k is because it's either true or not feature. And the and then choose k is because it just wants to pick k of them.
Your second part of your argument is right. The first part was not. So let me illustrate the answer here. Again, we can do the same sort of thing. I have a k conjunction. Let's say a k conjunction is exactly k features. Not less than k, not more than k, exactly k features. So that means I have k slots to fill. If I have a 3 conjunction, I have exactly 3 slots to fill. I have a bag of n features. First, I need to choose which k of them I'm picking. So how do I choose 3 things out of n? N choose 3 and choose k. So n choose k. And now I've chosen my k features. Each feature can either show up or be negated. Let's say I pick x1, x7, and x41. x1 can be present or negated, x7 can be present or negated, and x41 can be present or it can be negated. Each slot can be filled with 2 things. There are 3, and in this case, there are 3 things. In general, there are k possible things. So there are 2 power k times n choose k. So n choose k is to choose the k things, and 2 power k is to either decide whether it's negated or not. You got the second part right. You don't look happy.
Oh, I think that's what I was like trying to say.
Okay. So then you got the whole thing right.
No,
So the reason I'm not spending too much time on this is because I want to go back to the original point, which is how many mistakes will halving make on this? And it's the same game. You take log of 2 power k and choose k. We can be very, very loose with our approximation here. It turns out n choose k is an ugly thing to take the log of. So let's take a crazy upper bound of it, which is n choose k cannot be more than n power k. So 2 power k, n power k, the log of that is simply k log n, order of k log n. Now, this is interesting. I have n features. Think of n being something like a billion features. I don't know which feature is relevant. I have thrown in everything into the problem. But my task involves only 17 things that are relevant. So what is interesting here is the number of mistakes that are made is linearly dependent on the number of relevant features and only logarithmically dependent on the dimensionality. So let's see what we can infer from this. The first point, it's a mistake bound algorithm. It's a mistake bound learnable concept because log n is less than a polynomial. So in the dimensionality, halving makes fewer than polynomial mistakes. So it's clearly mistake bound learnable concept. The second interesting point is halving makes the number of mistakes halving makes is only weakly dependent on the dimensionality. Log of a million is not a huge number. It's strongly linearly dependent on the number of relevant features. So the difficulty of learning, the number of mistakes that are going to be made, depends more heavily on the number of things that are relevant, which is a nice property to have. If instead of that, if it was strongly dependent on the number of features, then adding more features is going to make learning harder and harder, even if they are not relevant. Halving is kind of cool in this sense. But halving is not efficient, and the challenge now is there an efficient algorithm that can match this bound? Is there an efficient algorithm that can make only a logarithmic number of mistakes in the dimensionality, and it strongly depends on the number of relevant features? We haven't answered that question, but does the question make sense? There's one other class of functions that I would like to explore here, which I have accidentally deleted the slide, so I will just write it up. Let's now consider the set of all possible Boolean functions. So the concept class C is the set of all possible Boolean functions. How many Boolean functions exist if you have n features? We've seen this before. Yes. Number of, or the size of C is 2 power n. Why? Because there are 2 power n rows in the truth table, and every assignment to a row is a different function, or every unique assignment to all these rows is a different function. There are 2 power n possible assignments, things to assign, and each one can take 2 values. Log of the size of C is still 2 power n. Exponential. That means the set of all possible Boolean functions is not learnable under the mistake bound model by the halving algorithm. And because the halving algorithm is optimal, there is no other algorithm that can make fewer than these many mistakes. So if your concept class is the set of all possible Boolean functions, you are out of luck. This is another slightly more rigorous argument for why it's important to restrict the hypothesis class. Because if you pretend that nature has the freedom to choose any function, then the number of mistakes you're going to make is 2 power n. And 2 power n is exactly the number of rows in the truth table. Which means the number of mistakes you're going to make is equal to the number of examples that can exist in this problem. Which means nature has to reveal that you have to, every time you make a prediction and you make a mistake, the only way you can quote unquote successfully learn is if you see every single example. Not a good situation. Let's pretend that nature does not have the flexibility to pick any Boolean function, and instead it's allowed to pick only a subset. Like, for example, all conjunctions or K conjunctions, something that's more efficient, not because nature is actually constrained that way, but because that's pretty much all we can search. Any questions? Yes.
So to clarify, this applies only to mistake bound online algorithm.
That's a good question. That's a very good question. The question was, I said Boolean functions are not learnable. But really, the complete sentence is Boolean functions are not learnable under the mistake bound model of learnability for today. Sometime later, in a few weeks, I'll point out that there's another model of learnability. Turns out all Boolean functions are not learnable there either. Turns out, however you analyze these things, this number is so large that we're not going to have any luck. Boolean functions in any model of learnability, turns out, are not learnable. But that's a good observation. I said Boolean functions are not learnable, but actually it's not learnable under the mistake bound model of learning. That's all I have shown today. Yes.
So correct me if I heard you wrong, but because the set of all possible Boolean functions is not learnable under the mistake bound model, that's why if we want to learn under this, we constrain our set C to a smaller subset.
Yes.
Okay.
Yes. We pretend that nature is not going to be adversarial and choose from any Boolean function. It's going to pick a subset.
Okay.
All of this discussion is in this pretend universe that we care about learning Boolean functions. Of course, if you think about functions like ChatGPT or what's the latest today, DeepSeek R1, it's not all Boolean functions. It's something much more complicated. But even for this class of functions, we see this observation that it's important to restrict the set of functions. Yes.
It's not learnable only for when n is large, right? For small.
Of course. Yeah. Yes. Sure. As n gets large, I would argue that in most interesting problems, n is going to be large. If otherwise, you can brute force. And in this case, what happens is even if n is small, in this particular example, let's pretend that n is small. Let's say n is 4. The number of mistakes is 2 power 4. 16. Doesn't seem like a lot, but there are only 16 rows in the truth table. So that means halving algorithm can make as many mistakes as there are rows in the truth table, which means what's the point of learning? Learning is about generalizing to unseen rows in the truth table, unseen instances. But if you have to actually see every single example that can exist, there's no notion of generalization left. Okay, I want to go back to this point now about K conjunctions, because there's something interesting here which we left unanswered. With K conjunctions, the number of mistakes halving makes is order of K log n. But halving is inefficient. Can we learn this efficiently? And this question, turns out, is intimately connected with a discussion about the choice of representation of your hypothesis and the difficulty of learning. Do you choose to search over the set of all K conjunctions? Do you choose to search over a different set? And how that changes the difficulty of learning. So, to kind of seed this conversation, let's say that you want to learn a conjunction. Should your search space also be conjunctions? Seems like a strange question. Let's say nature tells you that the true function it picks is a conjunction. And now you're going to instantiate a learning algorithm. Should your and learning is search over functions. If nature has told you that the true function is a conjunction, will your learning algorithm search over the set of functions or conjunctions? Yes or no? If the answer is in the set of conjunctions, is that the set you're going to search?
The hypothesis space includes all the examples, and there's no general one.
Well, in conjunctions, we were able to show that the number of mistakes is only order of n. And so we don't have to reveal the entire hypothesis space. This seems like a trick question. You know, it's like saying, if you lose a ring under this tree, are you going to search under the tree? Yeah. Except something strange happens because of this theorem by David Hausler. It turns out that if your true concept is a conjunction, that's just another complicated way of saying your true function is consistent with a conjunctive concept. But they're saying that the true function is a conjunction. And you have n features, and you have a set of examples. And your goal is to find a conjunction, but not just a conjunction. You want to find the smallest conjunction that's consistent with these n features, with the data set. It turns out this particular problem is computationally intractable. It's NP hard. That means if you want to find a conjunction that's consistent with your data set and is also the smallest possible conjunction, it's computationally intractable. This is also true for disjunctions. I'm not going to prove this to you, but the proof connects to, if you are familiar with this, the proof for that is connected to the minimum set cover problem. What this means is, if you want to learn conjunction and you want to add that extra constraint that says, I don't want any extra features in my conjunction beyond what is absolutely necessary, you're out of luck, because that is a computationally intractable problem. It's so strange. Your true function is a conjunction, and you want to find the smallest conjunction that agrees with the data set. It's not computationally feasible. Okay, that's the first observation. The second observation that I want to make is, in a previous lecture, we've already seen that conjunctions can be represented as linear classifiers. Conjunctions are linearly separable, disjunctions are linearly separable, etc. It turns out that if you, instead of exploring the space of conjunctions and trying to find a conjunction that's consistent with the data, you explore the space of linear classifiers, you can do that very efficiently. So the set of conjunctions, if you think of this point here, if this set here is the set of all conjunctions, the set of linear classifiers is something much bigger. Because of the theorem by Hausler, searching that smaller set is harder if you have this extra requirement that you want a minimum number of attributes. Instead, we can actually learn to explore this larger set much more efficiently. It's a bit counterintuitive. It's like saying if you lose a ring under a tree, it's harder to search under the tree and find the ring, but if you search the entire park, you'll find the ring. Combinatorial spaces can be counterintuitive sometimes. We will encounter a variant of this problem once again when we talk about pack learnability, which is it's a slightly more disturbing version of this thing. I don't want to dwell on this point too much, but this is a reason for thinking, let me not now go around inventing a new learning algorithm for conjunctions, a new learning algorithm for disjunctions, something for M of n functions. I have this other set called linear classifiers, which contains conjunctions, disjunctions, everything else. Maybe I should just try to invent a mistake-bound algorithm for linear classifiers that works for any linear classifier. If I do that, I get conjunctions and disjunctions and everything for free. And if I can prove a mistake-bound theorem for that, life is good. Right? Any questions about this plan? So what we have seen so far, or what you should know, is you need to know what the mistake-bound model for learnability is. The idea, the simple protocol where an example shows up, you make a prediction, the learner makes a prediction, and if there's a mistake, it updates itself. We've seen these two proof of concept algorithms, something called CON, which makes as many mistakes as there are functions in the hypothesis class. Another algorithm called halving, whose mistake bound is log of the size of C. Halving is interesting because you can use that you can apply that to different classes of functions to get a sense of, is this thing learnable or not? But even if it's learnable, it sometimes is more meaningful to rather work with more expressive classes of functions, namely linear threshold units, because it contains all of these interesting classes. And if you can prove a mistake bound for that, then we are done. That's this is the plan for that we are going to instantiate right now. But are there any questions?